Hello everyone, welcome to the Innovation Lab. In this video, I'm going to be providing a detailed step-by-step tutorial on how you can build a super affordable, super versatile, constant current and constant voltage DC to DC power supply that you can use for multiple applications. And we're going to do that by showing you guys how you can synchronously parallel multiple of these affordable DC to DC boost converters. Alright guys, as I promised in the beginning, in this video I'm going to share everything with you guys. I'm not going to hold anything back, but you guys have to watch the entire video. So in this video we're going to go over the concept, the schematic, the testing. And as I said earlier, I'm going to be dropping all the lessons learned for you guys, all the stuff that you need to know to be able to be successful in this project. So the relevance of a DIY project like this is that you can really use a system like this to build a DC to DC converter system that you can use for your DIY project, or you can use them as high power, high efficiency, high current battery charging system. You can also use a DIY project like this to provide drive power to your e-bike project. You can use them to drive your audio amplifiers. You can use them to drive your high power LEDs. And for those of us who are interested in low voltage to high voltage solar charging systems, given that MPPT charge controllers are very expensive, you can really experiment with something like this to see if it is something that's going to work for your project. Alright, I've added multiple chapters to this video to help you guys navigate the content. But one thing I would like to say is that as I was going through this project, there were lots and lots of lessons learned. So what I've done in this video to help you guys, to encourage you guys to watch the entire video, is that I added what I call the success tips. So those are the lessons learned that I added in form of the tweaks and tricks that you need to know to be able to be successful in doing this. So guys, I highly encourage you guys to watch the entire video. When you guys watch the entire video, that will send a signal to the YouTube algorithm that this is a good video to recommend to other people. And by doing that, the video is going to perform well. And guess what? When the video performs well, it encourages us to do more for you guys. So in a way, it's a win-win for everybody. Also guys, the Innovation Lab is now on Patreon. So becoming Patreon supporters will go a long way in helping us to get all the materials, the resources that we need to keep these videos coming to you guys working on these projects. So if you guys can support us on Patreon, that would be wonderful. All right, my friends, there is more to come on this project and also future projects. We're heading into the summer and I'm planning to do some more solar projects and experiments for you guys. If you like to see all of this, don't forget to subscribe to the Innovation Lab so you get notified as we are releasing all these videos. Big thanks to those of you who have already signed up and supporting us on Patreon. All right, so now let's jump right back into the video. All right, our setup is complete. So let's take a closer look to see what we have on the setup here. We have our 36-volt battery system here, and this battery system is a combination of our 12-volt lead acid battery system and our 24-volt lithium iron phosphate battery system. Guys, I'm only doing this because I am testing this system, and that's really all I have. I need a battery system that can give me high output currents at a higher voltage, so I had to rig up something like this. I highly discourage you guys from doing something like this at home. This is a very short duration test, and I am very closely monitoring the battery system, temperatures, looking at the voltages, looking at everything. So I don't encourage you guys to mix and match battery systems just like this. Again, this is for testing purposes. All right, so going from the battery system, then we have 36 volts coming into our synchronously paralleled DC to DC converters here, as you guys can see, 1, 2, and 3. And from there, we go to our control board. So the function of the control board, as the name goes, is to essentially control the PWM going to the synchronously parallel system. It's going to be looking at the output voltage levels. It's going to be looking at what's going on at the input, and it's going to use all that information to decide the PWM duty cycle that it is going to send to the synchronously paralleled converters, as you guys can see here. All right. So going from there, all the outputs, as you guys can see, are connected in parallel. All the positives are tied in parallel, and all the negatives are tied in parallel. And all of that goes through our digital power monitor here. This digital power monitor is not really necessary, but I use it to keep an eye on things. It's slightly off by a small factor, so that's why I'm using our DMM here and the current clamp here to look at the output power, the real output power that is going to our load. And I'm using the same setup here at the input, current clamp, and the input voltage measurement DMM to measure real time how much power is coming into the converter system. All right, so one of the questions we get all the time is, why is it so difficult to connect individual DC to DC converters in parallel? Why can't they behave like battery systems that we can easily connect in parallel and have them drive a common load? So I'm hoping that what I'm about to explain to you guys on this setup, what we have done, will kind of capture that. So the reason why it's so difficult to connect multiple standalone converters, as you can see here, in parallel, kind of boils down to a concept known as loop response or loop stability. So what happens with DC to DC converters is that every single converter has a control circuit, and this control circuit constantly looks at what's happening at the input side of the converter, what's happening at the output side of the converter, and it uses all this information to adjust the PWM signal that is driving the MOSFET, that is driving the power inductors. So that way the converter system will keep adapting to the applied load and stabilizing the system. So going back to the reason why they have a problem working together in parallel is because when you have more than one converter, so each of the converter on the network, as you guys can see here, will have its own control circuit. As you can see here, this is converter 1, this is a control circuit here, this is converter 2, this is a control circuit here, this is a converter 3, and another control circuit here. So with all these control circuits, you're always going to have a slight variation in their response times or their loop response or loop stability. So what that means is that when you apply a common load, each of these converters are going to respond differently. So the converter with the fastest loop response, we want to kind of dominate all the others, and by doing that it can self-overload, and when that happens, that converter is going to die, and another one will take over and possibly die, and the last one will take over and possibly die, because the idea is that the overall load on the system is going to be too much for one converter to carry. So what we have done here at a very high level of explanation is to create a converter system that kind of is analogous to a brain-muscle relationship. And in that relationship, we have a control board here that is dedicated to solely controlling the 3 other converters that we have here. So how we accomplished that was that on this board here, we removed the power section of this board and we left the PWM control section. As you can see here, this is the TL494 circuit and everything that is needed. And on the other hand, on the 3 converters here, that's going to be doing all the heavy lifting, the muzzle per se, you can kind of see that we have removed all the brains here, all the control circuits, and we're essentially tapping the PWM pulse width modulation control signal from this board here, and we are feeding that to each of the power boards over here, as you guys can see here. So this is power board 1, so the PWM goes to pin 9 and 10 here. This is power board 2, the PWM goes to pin 9 and 10 here, and the same thing is applicable to the power board 3 over here. Yeah, so this is the high level summary of this hack. So this board is the brain, and it looks at what's coming in, what is the power coming in, what is the load, and how it knows what's happening at the output is by looking at the output voltage of the converter network, and it looks at the output current through the network of paralleled shunts that you guys can see here, and it uses that to talk back to the control board and tells it, okay, right now we are seeing this much load, so set this duty cycle for the PWM to be able to drive that load. And now when it sets the PWM signal, the duty cycle and everything, so I am now picking up that PWM through this cable here, and I built this breakout cable as I was showing earlier, and I'm sending the same exact PWM signal to each of the converters 1, 2, and 3. So they're seeing the same exact PWM instruction or PWM signal. So I hope that this captures the high level explanation of why converters cannot work well in parallel without us having to do something as crazy as this. And I'm going to be able to explain more when we get to the schematic overview chapter of this video. So I'm going to take a quick pause here to explain what we have going on this control board. So what I've done is to add all these connectors. So to help me quickly disconnect the board from the setup if I need to go troubleshoot it. So I have the input voltage connector here, and the goal is to sense the system input voltage, so that way the control board is going to know what's going on in terms of under voltage protection. So for this board to function, all I really need is about a 3 amp or 5 amp fuse, and that is what we have here. And going from there, we have our frequency adjustment potentiometer, and here we have the output voltage potentiometer. I just moved it out to my control unit over here, and here we have our output voltage connector. Again, the function of this is to tap the output voltage that's coming out of the converters over here, and the control board again will use that to make a decision to know what's going on. And here we have our output current sense connector. So what I've done for convenience of this setup is to build this breakout connector here, and each of these connectors are going to connect to each of the converters. As you can see here, converter 1 and 2 and 3. So the white wire goes on the output negative that's going to interface with the load, and the black wire goes to the back side of the negative that's going to interface directly with the converter. All right, so going back over to the board, so the blue and black wire here is going to be our PWM control signal breakout cable, and I had done this to enable me to see if I can parallel up to 4 converters. For our setup here, we're only paralleling 3 converters, and as you guys can see here, the blue wire is tapping the PWM signal from pins 9 and 10 here, and the black wire is the negative or the return, as you can see here. So the PWM control signal from the breakout cable here is going to interconnect to each of these converters through these connectors. As you guys can see here, this goes to the first converter, and this here goes to the second converter, and this connector here goes to the last converter on the network. And I'm going to be able to provide a little bit more information as we go over the system design schematic. One of the major lessons I've learned as I go through this design is that this system likes to have a low impedance or resistance path between the output negative of the control board and the output negative of all these converters. So what I've done is to use a 14 gauge wire to go from this output ground here to the output ground of all these converters. So doing this helps the control board to correctly estimate the output current that is being delivered to the system, and it does that by looking at the collective voltage drop across all the output current sense shunts, as you guys can see here. So this is the first one, second one, and the third one, and everything is kind of tied in parallel and feeds back to the control board here. So if you don't have this cable connected, it kind of throws off the reading of the control board. So initially I was pushing about 2000 watts out of this unit and I couldn't exceed that. So it ended up being that I had to do this. All right. So one very important device that I added to the test setup is this solid state relay here. And the goal for that is to help me to seamlessly bring in the load without having to worry about any bounce effect of using a mechanical switch like this. I realized that using a switch like this to switch in a heavy load, whether at the input or at the output, kind of adds some unwanted transient voltage spikes. So being able to add this solid state relay actually solves that problem. So you can see that as you turn it on, the load will just come in very nicely, no transient spikes. And if you turn it off, it just goes out. This is quite impressive. So that was the only major addition that I added from the last test setup that we had. So we're still using the same kind of load. So these are resistive water heaters. I actually have about 4 of them connected in parallel to make sure that we're going to be able to put more than 3000 watts of load on the system. And what we're going to do is to slowly increase the output voltage that's going to come out of the converter system. And by doing that, given that this is a purely resistive load, the power dissipated on the load is going to be proportional to the output voltage of our converter system. All right, so let's go ahead and take the system for a spin and see how well it's going to perform. All right, so let's look at how our paralleled network of converters are performing in terms of load sharing. Now we have the system at maximum output load, at least at this point. So we can see that the system is delivering about 40 amps to the load. All right. So converter 1 here. So converter 1 is delivering about 10.3 amps to the load. Converter 2 here is delivering about 16.6 amps to the load. So converter number 3 is delivering about 12.6 amps to the load. So what I've seen running the system is that if you leave it for a while for the system to stabilize temperature wise, they will begin to even up the load sharing. Alright guys, the last thing we're going to look at for this test is the input and output ripple response. I know that this is something that a lot of you guys have requested. So let's go ahead and check out how the system is responding. So what we have here is the input is on channel 1 and the output is on channel 2. Alright, so let's go ahead and increase the load on the system and we check again at max power. Alright, so let's do a run stop so we can take our time to analyze what we are looking at here. So looking at our capture here, what we can see here is a peak-to-peak of 2.48 volts on channel 1 and the peak-to-peak ripple of 7.6 volts on channel number 2. And for the RMS, we are seeing a ripple voltage of 262 millivolts on channel 1, and on channel 2 we are seeing 325 millivolts. So guys, in my opinion, I believe that the RMS ripple that we're seeing on this system, on the input and the output, is quite low. So these measured ripples should really be below a 1% ripple on both sides. So having that at the back of my mind, I am convinced that the performance of this system is quite impressive. Also guys, given that I don't know who is in the audience and who is going to be watching these videos, so I feel like I have to explain every single thing. So what you guys just saw is an AC coupled measurement of the output. So I don't want you guys to think that the output is quite noisy. It is not noisy. So we're zooming in to look at the tiny little ripples. So what you're seeing here right now is actually how the input and output voltage rails of the converter system looks like. So it's quite clean and the converter system is actually performing very well. So channel 1 is the input voltage and channel 2 is the output voltage. So one of the things I've learned kind of the hard way that damages these converters or causes them to fail is the power on sequence that a lot of times most of us don't think about. So always try to bring up the converter system with no load applied. And on the input side, what I recommend you do to bring up the converter system is to add a small inline resistor to the positive of the system. So that way it helps us knock down the inrush current that could hit the converter and damage the drive MOSFETs or any sensitive components on the converter. So what I found was that bringing up the converter system with a small inline resistance to charge up the input caps of the converter system, and right after that bypassing out that resistor actually helps out a lot. And if you have a bigger resistor value that you can use, that even makes the inrush response much better. Alright, so let's go ahead and dissect what we have done on this design, and we are also going to be able to do a schematic overview in the end. So I've kind of explained what we've done here during the test setup overview. But on a very high level, what I've done is to add a whole bunch of connectors to this board to make it more convenient for me to move out all the signals or tap all the signals. So here is the input voltage connector. Here is the frequency adjustment circuit. Here's the output voltage adjustment connector. Here's the output voltage connector, output current sense connector, current limit adjustment connector, and the two wires here is for us to tap the PWM control signal from the TL494 on this board. And as you can see, we are tapping that from pins 9 and 10, and the black wire is simply the return. So this is kind of a simplified drawing of the control board. So the main components that we need to look at on the control board is the TL494, the UVP adjustment, the current limit adjustment, and the voltage adjustment potentiometer. Yes, we moved out the voltage adjustment trim potentiometer and the current adjustment trim potentiometer, and we're going to remove this current sense shunt here. But one thing I want you guys to know is that these functions are still on the control board regardless. All right, so let's go ahead and look at all the components that we had to remove from this board because we don't need them or because we needed to actually remove them to be able to implement this function. All right, on the PWM control board, so these are the components that we removed. We removed the power inductor because we no longer need the power section. We also have to remove the drive MOSFET, the rectifier diodes, the current sense shunt. Also, this board comes with 4 input capacitors. Since we are no longer using it as a power board, we removed 3 of those capacitors just to save them. And the same thing applies to the output capacitors. We removed 2 of them because only 1 will be sufficient. So the same thing applied to the input fuses. Actually, I removed all the 20 amp fuses and just installed 13 amp fuse there because that's what we need. So for you to be able to adjust the switching frequency of the control board, you actually have to remove R22 and change it to the value that will give you the switching frequency you need to optimize your design. On the control board, removing or replacing R22 is optional, and this is because you only need to remove it if you're going to redesign your power inductor like I did here. And by doing that, that also means that you have to tune the switching frequency of the circuit or the system to optimize the performance of your DC to DC boost converter system. So in a nutshell, after implementing all the changes, this is what you should end up with. This is what your control board should look like. So you're removing all the components that I mentioned, and you're removing R22 and replacing it with a system that looks like this. And this is for if you want to be able to vary the switching frequency. If not, you could just calculate the value of R22 that's going to give you the switching frequency you need and just drop that in here. And I'm going to cover that in the next slide. So as you guys can see here, this is the formula for calculating the switching frequency of the PWM controller. So one thing to take note here is that if you left CT the way it is, and CT is the capacitor that's connected to pin 5 of the TL494, so you just leave that alone, that should already be at 1 nanofarad. So the only thing you need to change will be R22. And if you kind of solve that through this equation, so you can kind of come up with the value of R22. So from my calculations, it needs to be below 50 kilo ohms. So you can use a trim potentiometer, which is essentially a variable resistor that allows you to tune that frequency within the range that you want. For the switching frequency that I'm using on this network, I realized that you could just replace R22 with 30 kilo ohms, and that will give you a switching frequency of about 36.7 kilohertz. All right, so for the synchronized power boards, the only thing that you really need to remove will be the TL494 chip. So that allows you to really use the PWM control signal that is coming in from the control board to tell these boards what to do. And finally, let's go ahead and look at the overall system schematic. So I've taken some time to make this as simple as possible. So if you're able to configure your control board and your sync boards, building this should be as easy as ABC. So as you can see here, this is the input power supply that you're looking to boost. Here is your output power supply that goes to your load. So the blue wire here and the black wire. So these are the PWM signal breakout cable that's going to go from the control board here, pin 9 and 10, and spread out to the sync boards, pin 9 and 10, as you guys can see here. So going to the output side, here the white wire and the black wire is the current sense breakout cable that's going to transmit all of that information back to the control board. That way the control board knows how much load we have on the output. The same thing applies to the output voltage line here. So this yellow and black wires here goes all the way to the output. So that way the control board sees the output voltage of the boost converter system. On the input side, the same exact thing applies. So we're tapping the input voltage that comes into the system, and by doing that also the control board knows exactly what is the input voltage level, and this is mostly useful because the control board needs to be able to make a decision. So this is it in a nutshell. So if you follow this schematic exactly how it is laid out here, you should really be able to replicate this entire design. So one last thing I would like to mention is that, as you guys can see here, I added this black line here, and I explained it earlier when we were going over this test setup as a success tip. So make sure that you guys use at least minimum of gauge 14 to tap this current sense return back to the control board. If not, you're going to be struggling with pushing out the amount of output power that you desire from this design. Alright everyone, we have come to the end of the video. I want to say thank you guys for watching our videos. Thank you for supporting us. And as you have seen in the video, this system works quite well. And being able to do something like this gives you high power, high output current that you can use for multiple applications. And honestly, I believe that we can still get more power out of this system. So right now, the battery systems that I'm using is kind of limited to about 100 amps. So that also limits the output power that I can push through the boost converter system. Also guys, the Innovation Lab is now on Patreon. So if you guys can become our Patreon supporters, that will go a long way in helping us with all these innovations, all these tests, all these projects that we're working on. So being able to support us on Patreon is going to help us with keeping this channel running, because the videos that we make are kind of resource heavy and time heavy. So this will go a long way in helping us keep everything running, keeping our website running, and we'll greatly appreciate it. All right, my friends, I'll see you guys in the next video.